latch, you can either have a negative base latch or a positive base latch. So the multi-base latch is level sensitive. So let's see here. So the D is the input and this is the clock. So the clock will toggle between 0 and 1. Okay, so let's look at what happens here. So when the clock is high, the D, the Q will not have anything. It will have the value of high. So this multiplexer is active low. So whenever the clock is 0, then the output will go through. The Q will follow the D. Okay, so when clock equals to 0, Q equals to D. Right, so you can see here, and whenever the clock is 0, the output will follow this D. And for the positive base latch, when the clock equals to 1, Q equals to D. So here this is 1, 1, 1. So at this point the Q will follow the D, otherwise Q equals to 0, and this else Q equals to 1. Okay, for a CMOS SR latch, right, let's see what happens here. This is the implementation of a set reset latch. The set reset latch, as you can see here, this is the truth table. Okay, so if the S is high, that means the Q is high, and if reset is high, then the Q is 0, right? And this is an indeterminate undefined state if both are high, and if both are 0, then it will store in the previous value, right? So okay, so when this is a NOR gate, so a NOR gate, A, B out, 0, 0 is 1, 0, 1 is 0, 1, 0 is 1, 1 is 0. Okay, so the NOR gate can be implemented as this in the complementary CMOS version. It will be 2 parallel NMOS and 2 series PMOS. Okay, and these are connected back to back. So let's see what happens when set is 1, set is high, so this one is on and this is off. Okay, so this output here, Q bar will be pulled down to 0, so this is 0, and this is off, so there will be nothing there. This is 0, and this one will turn on, and this is off. Okay, so if this one is on and when set is 1, R is 0, so this is also on. So this is on and the Q will be high, right? So this will determine this state, right? So this is agreement with this. Set is 1 and reset is 0. So this set is 1 and reset is 0. Q bar is 0 and Q is 1. Okay? So if both set and reset are low, let's look at the next state. If both set and reset are 0, so this is 0 and this is 0. So this is off and this is off, right? So this is open and this one is on. Here this is on, but this one we do not, if this is broken here. So the value will be stored in the latch here. The value will be stored in the node here. Okay, so the latch holds the existing state indefinitely. If both set and reset go high, so this is high and this is high, so these are pulled down, so this is 0, and this is also pulled down, so this is 0, right? So this will give it an indefinite state, because this is 0, this is on, and this is 0 and this is on, and this one is 1 and this is ground, so it doesn't know whether it needs to go up or down. So this is an indefinite state, so this Rn equals to S equals to 1 is not allowed. Okay, so the gate level symbol is shown here with the NOR gate, and to estimate the set time and add time to discharge. So how do you estimate the set time? You just add the time to discharge Q dash and the time to charge Q. So what is the clock latch on the NOR version? The clock latch here means that the NOR-based latch is added with a clock input. So the latch is responsive to the input S and R only when the clock is high. So let's look here. When the clock is high, this is 1010. So only when the clock is high do we consider the output. So when clock is high, S is 0 and reset is 0, so it will store the previous one. When set is 1 and R is 0, so Q is 1, right? And the next clock cycle, when it is high, set is 0, reset is high, so the output is 0. This is 0 1, and when set is high and the reset is 0, so you have a value of 1. And this is the next point. When reset is 0 and set is 0, it will store the previous value. This is the previous value. And when set is 0 and reset is high, that means you reset the value back to 0. So the timing diagram shows the level sensitive nature of the clock set reset latch. Note 4 times when the Q changes state when the S goes to high during the positive clock, and on the leading edge after the changes in set and reset during clock low. There is a positive glitch in S when clock is high. This is the positive glitch when clock is high. This is the glitch, and it sets the clock to high. And when reset goes high during positive clock, and when the reset goes high, the output will be 0. Next is the JK master slave flip-flop. A flip-flop is defined as 2 latches connected back to back, and the first latch is the master and the second latch is the slave. And this is the slave. So there are basically 2 latches connected back to back. It eliminates transparency, or the change in occurring in the primary inputs is never reflected directly to the output, since opposite phase clocks are used to activate the M and S. So the first master is activated by clock and the slave is activated by clock bar. A JK master slave flip-flop is shown below, and there are feedback paths from Q to Q bar. Here, this is Q and Q bar. It does not exhibit any tendency to oscillate when J equals to 1 and K equals to 1, no matter how long the clock period, since the opposite clock phases activate the master and slave separately. The NOR-based version can be done with 2, 4, and or inverter CMOS gates requiring 28 transistors. It can be susceptible to once caching that is the positive glitch in either J or K input while the clock is high, which can change the state of the master latch and the slave latch on the next edge. So it can capture any glitch from J and K whenever the clock is high, just as we saw in the previous slide. So this is the glitch, right? If you have back to back, you can still store these values. And when there is a glitch, as you can see here, the glitch is a 1, so the value 1 is stored inside the latch. Okay, another step is the D-Latch implementation in CMOS. So as you can see here they use transmission gate. So what is a transmission gate? A transmission gate is a gate that can pass through 0 or 1. So this is the transmission gate. So let's explain the transmission gate. So let's say you have a transistor. This is in and this is out. Okay, so if in is 0, right, and you have in, and this is the clock, right? If in is 0 and clock is 0, what happens? So here this is the output. If the clock is 0, that means this gate is open, so the input cannot go out to the output, so your output is undetermined. Okay, whereas here, if okay, let's change here the input. So if clock is high, the gate is on, so the gate will pass through whatever is the input. If the input is 0, the output will be 0. If the input is 1, the output will be 1. So the clock, the output will equal to input when clock equals to 1, and otherwise out is undetermined. Okay, so transmission gates, as you can see here, the NMOS transmission gate can pass a 1 very good, and the PMOS transmission gate, so the PMOS transmission gate is the opposite. This is the in and this is the out, and this is the clock bar. So in, clock. When the clock is 0, clock bar is 1, so this transistor is off. Okay, when clock is 0, in is 1, you have undetermined. But when clock is 1 and clock bar is 0 here, so in will pass through. So it doesn't matter where in is 1, so then it will be 1. If in is 0, then the output will be 0. Okay, so as you can see here, the PMOS transistor can pass the output whenever the clock is 0, and the NMOS transistor can pass the output whenever the clock is high. So because of this, if you have a transmission gate, you can transmit 0 or 1 very nicely. Okay, so this transmission gate can be used for the D-Latch to minimize the number of transistors. So if you see here in the normal implementation, a NAND gate an AND gate consists of a NAND gate plus an inverter. So this is 4 transistors and 2 transistors here, so a total of 6 transistors. This is 2 transistors and this is 4. So the total here is 12 10, 12, and another 10 here. So 22 transistors. If you implement, using transmission gates, you can reduce the number of transistors into like this: 1, 2, 3, 4, 5, 6, 7, 8. Only 8 transistors. Okay, this is 22 transistors using CMOS logic, and this one is using 8 transistors using pass transistors. Okay, so the D-Latch can be normally implemented using transmission gate switches as shown in the left, and the input transmission gate is activated when the clock is high, while the latch feedback loop transmission gate is activated when clock is equals to 0. Alright, so the input is accepted when the clock is high. So let's say if the clock is high, 1, the clock bar is 0. So here the input, whatever the input is, let's say the input is 1, it will come out here as 1. So if this is 1, this will be 0, and this will be 1. This is 1, clock bar is 0. Sorry. And clock is high, but this is 0 in an NMOS and 1 at a PMOS. So this will be open. So the output will be 1. So when the clock becomes low, here 0, this is 1. As you can see here, this is open and this is open. So even if you have an input, you don't know when you get the output. This clock bar is 1 and clock is 0. So this will be on and this will be on. So this input here, we did not know what it was. It will go out here. So what was the input? It will take whatever the previous input was and bring it out there. So this here, this path will go as a feedback loop and will store the data. So this, when the clock is low, the output will have the previous data.